The minimum gauge.
Sorry, say it again. There was somebody talking here.
The minimum gauge.
The gauge freedom in E&M.
Lorentz gauging and that kind of thing, right?
Yeah. So let's see. I got thrown. I had forgotten to turn on the recording, and I just turned it on, and this voice comes on and says, "Recording in action" or something. You look at the homogeneous Maxwell equations, and they're the ones that tell you that a potential exists. So let's look at that a minute. Just develop the whole picture of the gauge invariance within Maxwell. So what we've got is that the divergence of B is 0, and we have that the BDT plus the curl of E is 0. And the Poincare lemma and its converse, and actually its converse here, tells us that in suitable regions, a vanishing divergence means that we can write a vector as a curl of something. So we do that, and that's how we introduce the vector potential. This is true. Technically, you can use this theorem converse to Poincare. Poincare lemma is d squared equals 0. So the converse is that if d of some form is 0, then omega is d of something, which allows you to integrate the equation. That, of course, depends on boundary conditions and things. So, we know these aren't quite equivalent, but we're working in R3 and stuff here, so we don't really have to worry about that. So we write B as the curl of A, and then if we put that into the equation for E, we can write the whole equation as a curl of A dot plus E. And that vanishes, and now we invoke the same theorem to say that if we have a vanishing curl, then the thing must be a gradient. And so we can write E plus A dot as minus is conventional here, but minus the gradient of something. And that says that we can write E as minus grad phi minus A dot, and we can write B as the curl of A. So that's how the homogeneous Maxwell equations give us the existence of the 4 potential for E and M. Now the converse is immediate, because if I take the curl, the divergence of the curl is 0, and if I write this expression, it will hold. So going back the other way is no problem at all. Now, this is not unique. We have already mentioned boundary conditions, but really our starting point here is key, because if we write B as the curl of A, then that's arbitrary up to curl of what vanishes. Well, a gradient. So if I change A by a gradient of some function f, then B doesn't change. That leaves B invariant. So there is this freedom in the choice of the vector potential. Well, let's see what that does to E, though, because if we're going to muck around like this, we've got to keep both of these things unchanged. So this means that the new E is going to be minus the gradient of what? Well, let's allow phi to change too. We're allowing A to change, so we should also allow phi to change. Then here, subtracting A dot, okay, we have A dot, but now there's minus grad F dot. And we can write this as minus the gradient of phi tilde plus f dot minus a dot. And this is equal to phi provided phi tilde is phi minus f dot. So these two transformations, the spatial component changing by a gradient, the time component changing by a time derivative. So in general, A alpha, the new A alpha is the old A alpha. Let's see, what's our sign convention here? I think this is minus d alpha of this function f. Is that right? So yeah, if we raise the spatial index, that changes the sign with our current metric. So we have this freedom. Now I've got plus in the notes. Let's see why. Oh, because I've lowered a. All right, so ai tilde is going to be minus ai plus di f. Yeah, so that sounds like a minus, doesn't it? We could use minus f. All right, let's not worry about which way we write it. Either way, just take f to be minus that function. So let me see how I wrote this. We took a tilde to be a minus grad. Yeah, I did it with the opposite signs in the notes. Basically, the 4 vector A can change by the gradient of any function, the 4 gradient of any function. And let's see, let's define that function so that we add its gradient. So yeah, let's use this as our gauge transformation. We can certainly do that for any function, and that will not change E or B. It's always E and B that are, those are the physical fields. Those are things we measure. Those are not gauge dependent, and every physical effect needs to be able to be written in terms of those. And I want to pause and give you guys an example here that you find in books, and a great deal is made of it. The Bohm-Aharonov effect. People will sometimes try to convince you that, well, A is the photon field and that's real. And, it's not true. So, one example is you do a double slit experiment and you send light on the double slit, but now you put a solenoid here. And what happens is, okay, you get your interference pattern over here, but this pattern depends on the magnetic field. So you've got a magnetic field inside this solenoid, and by changing that magnetic field, you're going to shift this pattern. And what's happening is that, right, if you look at well, let's pick some curves that go around. So the effect on the phase, you get a phase difference here that is affected by basically integrating A along the path, and you get a similar effect here, A along the path. And so that shift in phase seems to depend on the integral of the vector potential along the path. But in fact, what you've done is to create a closed loop. So the net effect on the phase is a closed loop integral of A dot dx, or let's see more completely, A alpha d alpha if time were to come into it. But use Stokes theorem here. Now let's keep it three-dimensional. Stokes theorem, and this is equal to EI times the surface integral of b dot n d2x. So the actual physical measurable effect only depends on the magnetic flux, not on anything about the vector potential. Now, there's a further mystery here because the electrons or the photons are never inside the solenoid. So how do they know there's a magnetic field there when they never penetrate? You tuck this behind here, so there are there's basically very small probability that the field is there. Well, but that's the key thing. The position of the field is uncertain, right? Uncertainty relation. And so we don't know that the field is not inside that solenoid. And so it actually can penetrate the classically forbidden zone and sense the presence of a field, and the phases adjust accordingly. So there's no conflict here with quantum mechanics. There's no reality to the vector potential that's required to explain these effects. So don't let people tell you that the gauge is that the vector potential is a real thing. Potentials are only defined up to transformations. The Newtonian potential for a force, for Newtonian gravity, it's the gradient of the potential is the force. Well, that potential is arbitrary. You can add a constant to the energy, right? You've done an integration there. There's an additive constant. So the gravitational potential is not a physical thing. It's differences in the potential. Differences now are forces, and those we measure. All right, so little mini rant, all done. Let's see what this says now for the rest of Maxwell's equations. You guys have probably been through this, right? You've done like chapter 7 of Jackson, so you know all this, right? I'm going to run through it anyway, because yeah, we're moving steadily towards the cool stuff. Yeah, just yesterday I was putting some Feynman diagrams in the book. Where I've actually computed a scattering amplitude yesterday afternoon. Came out within a factor of what was it, 2 pi to the 8th. I had a few factors of 2 pi off that I've got to track down. But a simple scattering of 2 scalar particles involves 36 integrals. It's just, now they're in groups of 4 and they all give delta functions, so it's not really as bad as that sounds. But keeping track of it is fairly horrific. So you guys are in for some fun when we get another 20 or 30 pages down the line. So all right, let's look at the inhomogeneous Maxwell equations. Now we're keeping them homogeneous here. We're just looking at free electromagnetic fields at the moment. So we'll set this equal to 0. But in terms of the potential, this becomes minus del squared phi minus, what is it? A dot. So we're going to have divergence of A dot as part of this. And what we want to do then is, what do we want to do? Yeah, I know. I want to write this as a D'Alembert of phi, but I'm adding a second time derivative, so I'm going to subtract d squared phi dt squared, and then here I have divergence of A dot this. And this business I can write as a time derivative of d phi dt plus del dot A. You know, that looks, no dot. This looks a lot like the continuity equation or something. Well, it's actually a gauge condition, right? We can make that vanish by choosing the gauge right, and I'll show that in a minute. But let's here, let me write it more cleanly. I can write this as ddt of d alpha a alpha. So it's a covariant divergence of the vector potential. And now if we do the other equation, Faraday's law. So we've got, what is it, E dot minus the curl of B would be J, but again, we're in vacuum here. And we put in the potentials here. So E is minus grad of phi, but now we have phi dot because we have a dot. And we have, actually, this is going to be a double dot with a minus. And then the curl of B is del cross A. And I find this one worth remembering. The double cross product is, it's minus del squared of A. Well, I've got a minus, yeah. So it's minus del squared plus the gradient of the divergence. And then we have an overall minus sign here. So all of that. And now, what does this look like? Well, this part is minus box again. So I can write box of the vector potential, change the signs of everything. And what have we got? Let's see, that becomes plus the gradient of...
Or check, by the way.
Oh, thank you. So change the sign of the whole thing, and this becomes plus a box here. Then these two terms are plus, and they're both gradients, so I'm pulling out the gradient, and we have, guess what? Phi dot plus del dot A, the same thing. So this term is just like that term, but now a gradient. So we would like to choose F such that that vanishes in the new gauge, right? Then then we just have a pure wave equation for A and phi, and that's a nice thing. That's a simple equation to solve. In fact, you know, we're back to the Klein-Gordon field again. You know, we just write a Fourier expansion for the solutions. Well, we can actually do this because demanding this is demanding that d alpha of A alpha plus grad alpha of our gauge transformation has to be 0. And d alpha is a box. And what it says is that box of our gauge transformation needs to be minus d alpha A alpha, which is just some function g. We don't know what that was in the original gauge, but it's simply some function. And now all we have to do is solve the wave equation with a source, which you guys being expert in green functions can do. So there essentially is always a solution for F that will, in the new gauge, satisfy what's called the Lorentz Gauge condition. All right, that right there is the Lorentz gauge. So we're going to choose the Lorentz gauge. And in the Lorentz gauge, we have need of a better marker, but now that stuff goes away and this stuff goes away, and we have box of A alpha equals 0. And D alpha, A alpha equals 0. So this is a gauge condition, and imposing it makes a very simple wave equation out of Maxwell's equations. So look what we've done here. We've solved the two homogeneous Maxwell equations by introducing potentials. We can do that in any suitable region. Then rewriting the remaining two Maxwell equations in terms of those potentials, we find that we can choose, use our freedom in choosing the vector potential to make it satisfy the simple wave equation. So this gives us a very simple formulation of Maxwell's equations. This is a lot easier than all that del cross B stuff, right? We know how to solve wave equations. Okay, this is not all we can do. All right. Yeah, Jimmy York tells us that the gauge always strikes twice. And here it is. Did I tell you that before? I told you that before, didn't I? Yeah, well, the gauge always strikes twice. It's true, it really does. It's true, coordinate freedom in general relativity. Use it twice. SUN variation in gauge theories. You can use them twice. It always happens that you make some nice gauge choice and there's still some freedom. So I can ask, well, is there an A tilde that still satisfies this, but has some freedom where A tilde is this A plus some other function here, you know, this is a different function F. And so we still want to satisfy the Lorentz Gauge condition. We already satisfy it here. This is already 0. And what's left is box F. So I can go to a new gauge from a Lorentz gauge. I can further restrict the gauge if I restrict my gauge function to be a harmonic function, a solution to the simple wave equation. And that's enough to make, let's see, well, let's see if we can't get rid of the troublesome component, A0. So the 0 component of A, of the new A, changes by, it's the old component plus F dot. And if I ask for that to be 0, it says that F had better be the integral of A0 dt. Well, that always exists. And the only thing I have to worry about is box F. But box F depends on box A. And the Lorentz gauge is guaranteed that that's 0. So box F is 0, and I'm allowed to do this. And therefore, I can choose a gauge which is not only the Lorentz gauge, but also has vanishing time component to the vector potential. Whew. Okay, so far this is good. What if we, there's one further condition that happens. If A0 vanishes and we have the Lorentz gauge condition, that further implies that A satisfies the del dot A equals 0, the Coulomb condition. So this is called the Coulomb gauge. Okay. Now, suppose we start all this again in the with these gauge conditions. Then let's see the action. I have to remember what I was doing here. Why am I doing this? So yeah, we get the field equation. So yeah, let's write out the action. And just keep this gauge condition in mind. So an action is 1/4 minus a quarter f squared. Now we can write that out as yeah, if we expand this, AI dot. So we get the minus half AI dot, and then we have a DIAJ, DIAJ. So we've got a curl of this thing. We also have it the other way around, minus DIAJ, DJAI. So yeah, that's probably 2f squared. So we've canceled a 2 here. And if we vary this, we get rid of the half and we integrate both arms. Okay, so yeah, let me vary the action. So it's going to give us 2 of everything. So we have AI dot del AI, then here plus, yeah, I can think of this as DIAJ with FIJ. Just for it's symmetric, but I can write it as DI del AJ with the rest of this and a factor of 2. DIAJ minus DJAI. And now I get rid of the minus when I integrate by parts. I'm going to discard the surface term. So I get AI, this was dot, double dot. And here I'm going to get a wave kind of thing. Excuse me. Let me call this J and pull out a del A J here. Then the minus sign goes away here as well, so I get plus box A J minus DJ DI, interchanging the derivatives AI, and that guy's going to be 0 now. So, sorry, this was del squared. Sign is funny. Why is the sign funny? Oh, it's because, where'd it go?
So you distributed the the sign in from the front, which is going to get absorbed into your first term and then
yeah,
cancel.
I really want to, I do want a minus here somewhere, but the somehow, oh, okay, yeah, here it is, right there. DI is minus del squared. I get tripped up all the time on that that funny space-time signature. Okay, so this is box minus the gradient of a divergence. The field equation is just box A, well, box A vector minus grad div, like this, equals 0. So this is going to go away as a gauge condition, and then we get a pure wave condition. So now we can write plane wave solutions. Now, let's see. yeah. What our goal through the plane wave solutions is going to be is to recast the gauge condition. It's a differential condition. That's awkward. We want to make it an algebraic condition, but we can do that in momentum space. It makes it transverse. So let's just write a solution for A. We have in our combined Lorentz Coulomb gauge, we have box A equals 0. So we can let A be some vector e to the I. Am I just writing kx minus omega t? I think that's what I'm doing. Yeah. Or I could write that as e to the minus I k alpha x alpha, if you prefer that. And the full solution then, we need box A equals 0, and that tells us that k alpha has to be 0, and we're going to need d alpha a alpha equals 0, or sorry, just the Coulomb condition is what we really need further, and that's going to pull down a k, so that's going to give us k dot a0 equals 0. So in the momentum space, we're going to have this as an algebraic condition. So then, yeah.
Sorry, is there a second solution to the box equation? I'm just wondering why there isn't like a plus e to the negative 2.
Oh,
is that from the Coulomb gauge, or is there something magical?
No, let's see. Yeah, probably second solution. We want these to be real. So yeah, when I write out the general solution, I'm gonna.
Okay, you're fine. That's just
I'll put both of them.
I'm sorry. Thank you.
Yeah, this is just putting in a plane wave, and we get this condition. But yeah, we could have minus here. So let's see. This is going to look a lot like what we had for the scalar field, right? We have AI is going to be in. Let me just get my constants right here. Okay, we've got d4x, and then we're going to need a delta function of k alpha, and that'll split into a couple things, and then an amplitude that, all right, at this point still depends on omega and k with e to the I k alpha x alpha minus I plus a conjugate of omega and k e to the I k alpha x alpha. So there you are. Yes, we have both terms. And that is just a complex conjugate. And then we need the divergence condition. And what that's going to give us, d4x delta k alpha, it's going to pull down a ki in each case here. So we're going to have ki, well, there's a minus I on that. Ki ai, minus I k dot x. Increasingly, I'm going to write the 4-dimensional inner product as just k dot x. By the time we're doing path integrals with 36 integrals, we're not going to want to be putting indices on every x and p. And then here we have I k I a I conjugate e to the I k dot x, like that. Okay, so you see that we satisfy this if ki ai is 0. And so we're going to need that as an additional condition. I'm going to have to pick up some more use some more markers here. Okay, so now we want the Hamiltonian formulation again. We've chosen the gauge, so we're in a little better control of what the real degrees of freedom are. So we have now only 3 degrees of freedom. We've zeroed out the zero stuff, pi zero and a zero. So we're dealing with 3 fields, but we still have 1 subsidiary condition. So we're still going to have to worry about how to impose this gauge. So pi I now, and we only expect 3 of these, will be the variation of the Lagrangian with respect to the 3 independent fields now, AI. Oh, geez. I just erased the action. Yeah, sorry, what?
I was going to say, won't it be the time derivative of AI, since we're doing the Hamilton, since this is
that's right. Thanks. Yeah, that's right, Tyler. So let's see. I've this is boy. Okay, so we had AI up, AI dot up, AI dot down. So this is just going to be minus AI dot down. We had a minus a half, and we have an A dot squared basically. So that's pi, and then the Hamiltonian. Let's see. I'm wondering how soon I'm going to need this. I'm not going to need this very soon. Okay, let's just press on here. So the Hamiltonian is going to be the integral of, let's see, d3x pi 3 I dot minus, that's will be the density now. And that turns into, okay, so L's got a half pi dot here. So we're going to get our usual 1/2 d3x. So then we'll have pi I. I'm worried about signs. Yeah, that's right. And then, yeah, and then the AIJ stuff. Let's see which way to write it. So that's like half of an x squared, because we pulled out instead of a quarter, we have a half. Okay, so that's what the Hamiltonian turns out to be. And now we can impose the canonical Poisson brackets, AI pi j of x and y. And that'll be delta ij, but we're still in trouble. So this still has the same problem, right? It's not, we've gotten rid of the pi zero. That's okay. But we still have this gauge condition, right? We still need di ai equals 0. And that's not true here. That's going to give us a delta function of a derivative of a delta function. And this is not so good. But what we can do is put the whole thing in a momentum basis. You know, we've been doing a fair amount of that in quantum. Let's do it here. So on the right side, still need a better marker here. So we're going to fuss with this a bit. Instead of that, I want to write it in the momentum basis. So I can expand the delta function as 1 over 2 pi to the 3 halves d3 k. Well, hello, Ross. Hello, cat. Times e to the minus I k dot x minus y. So writing our delta function that way, the Poisson bracket can be written as, or the gauge condition, DI with pi j. Right? You know, this had better be 0, but here we're just going to pull down a k. So here we have a delta ij under the integral, and we're going to pull down a k j. We have a minus I, and so you know this doesn't work, right? But we can fix it. So, you know, this just gives a ki, but what we really want it to give is 0. The advantage is now that this is an algebraic condition, and it's easy to write projection operators. So if I have any vector vi, then if I want a projection in the v direction, I just write vij over v squared, and that acting on any other vector is going to be v dot x times v over v squared, which is, you know, unit vector. So that's the component of x in the v direction times a unit vector in the v direction. So this always gives me a projection operator that projects parallel to the given vector. To write a projection in the orthogonal direction, I just subtract that from the identity. So now I'm subtracting that and adding in the full vector again. So to get the part of x perpendicular to v, I subtract the part parallel to v. Now if I dot v into this, I get x dot v minus x dot v is 0. So it's very easy to produce a projection operator perpendicular to any given vector. And that's what we want to put here. So the Poisson bracket that we want to impose is ai pi j equals, and let me see how I write this now. Yeah, we're gonna write it with the 2 pi to the 3 halves, the integral d3k, and now instead of the Kronecker here, we're going to put pij. That's the projection orthogonal to k. I'll write it in a second. Then our delta function, even minus ik x minus y. So there we have a suitable set of Poisson brackets that satisfy the gauge conditions that we've imposed, where here pij is simply Kronecker ij minus ki kj, 1 over k squared, 1 over k squared ki kj. And if I hit that with a k, I'm going to get k here. I'm going to get a k squared there. I should probably worry about whether I want a plus or minus here, because kj is minus k squared. So I'll write it with a plus sign. With that signature in mind. That's not what I put in the notes, unfortunately. But essentially, I'm writing k hat, which an outer product of k hat with itself here. Okay, so that gives us a set of Poisson brackets with the actual degrees of freedom of the electromagnetic field. And there's one more condition we have to worry about. This is this was a of x and pi of y, but the right-hand side is symmetric in x and y. So if I take a y derivative of this thing, so if I've got ai of x pi j of y, and I take dj of that, on this side, I've got this integral of a projection pij, and this derivative is still going to pull down a k. It's going to pull down an ikj times the exponential. Well, that is still 0. So we have to have some condition here on a derivative of pi j, and what is it? It's Coulomb's law. All right, it is the divergence of the momentum. Pi, remember, is essentially the electric field. So this is the vanishing divergence of the electric field, and we still have that that one elusive Maxwell equation. So this is just what we needed, and it follows automatically by putting in the projection operator. And now we can expand A and pi in Fourier series subject to this condition. So I've erased it already. I'll write it again. I'm sorry, I've been talking too long here. I'm going to lose my voice before the end of the period. Now we just write it. Okay. So, any questions on all of this? Recap what I've done, right? So we looked at the theory, we ignored the vanishing pi 0, and things worked okay up to a point. But when we wrote the Poisson brackets, one of them was inconsistent. And so we went off and studied gauge transformations a little bit and realized that we can choose a gauge in which A satisfies the Lorentz and Coulomb gauge conditions. So the Coulomb lets us set A0 to 0 and work with just 3 degrees of freedom. And then finally, by going to momentum space, we were able to algebraically restrict the expansion coefficients of A, the mode amplitudes, to enforce the second condition. And on the remaining degrees of freedom, we have suitable Poisson brackets to quantize. So by going back, we've got everything we need to write the quantum theory. And oh my gosh, we're a hair's breadth away from doing interactions. All right, so what's it look like? And now, let's just suppose we do the integral over that delta function. I wrote this solution before with a delta of k alpha, and that's basically that's proportional to derivatives of omega plus omega. Let's see. plus the magnitude of k, or omega minus the magnitude of k. And so what we end up with is, as a normalization, the derivative of that gives us a root to omega k here. And now all the omegas I write are going to have, things just have k dependence now, because omega is dependent on k. And we have this, and then pi, we're going to pull down a minus I and pick up a minus sign and an extra omega. So pi I, where did I put the index here? Pi I. So we get an I over 2 pi to the 3/2. I think I want a minus I there. Yeah, let's put a minus here. So differentiating t here, I pull down a minus I omega. There's the minus I. The omega is going to give me d3k root omega over 2. And then ai of k, minus I k dot x. And a relative minus sign here, ai conjugate of k e to the I k dot x. All right, back k dot x with omega t positive. All right, now I give this one to you guys as an exercise. Invert that and solve for a and a conjugate, and it's a simple enough thing. It's a certain linear combination, the integral of a certain linear combination of a and pi, right? So just invert the Fourier transforms on both of those and take a linear combination that lets you solve for ai. And then you can probably just take the complex conjugate. Yeah, you can just take the complex conjugate of that to get ai conjugate. So now we impose the Poisson brackets, and let me see, where do I introduce? Oh, it's the next section. No, we might get to that. All right, so let me see. We want to find the commutators of these things. So yeah, don't worry, I give you the forms. So ai ends up being, so here's the answer to your exercise. Where'd it go? Yeah, 1 over 2 pi to the 3/2. We may get in trouble with my normalization. I think a lot of books use a different one. So d3x, this is a function of k of omega over 2. And then what is it? A plus I over omega. And a Fourier mode. So these are functions of x and t, and then we get an e to the minus I k dot x. Is this right? Oh, I wrote it as a of q. Okay, so yeah, and then the complex conjugate of that is the obvious complex conjugate. So what we want to do then is to work out the Poisson bracket of ai, and a convenient one to take is if we multiply in an extra I. So if I stick an I here, a conjugate, the j, then this is what we're going to have I times this. So we'll have I over 2 pi. But let's see, I'm taking 2 of these, so I'm betting I get a 2 pi cubed here. And then d3x, d3y. Okay, because yeah, if I write a of x, let's call this one. Oh, no, this one's going to be k. This one's going to be q. Let's say, but they're written as a Fourier series in x. Let me check a sign here. No, that's what I got. So, all right, I'll assume that's right. Then each of them gives. Actually, we have an omega k, omega q, square root over 2 here. We get 2 square root of omega over 2 factors. Is that right? Yeah, square root. Okay, that's good. And then we have to take the commutator of this thing with its conjugate. So times the bracket. And let's see, where is it here? A, I, and these guys are x plus I over omega pi I of x. Commutator with, let's see, we're gonna, let's put the J down. I hope I don't get in trouble because of that, but let's put A of y minus I over omega pi J. So those are the things that satisfy a Poisson bracket. And then we have exponentials e to the minus I k plus I q minus I k dot x plus I q dot y, like that. And let's see, do we have any other integrals? Yeah, okay, so we're going to get some integrals and delta functions from this Poisson bracket. Okay, so that bracket boils down to what? We're going to get 2 things here. We're going to get an AI with pi j, and we're going to get a pi I with aj. That's in the reverse order, so we can flip that, and it'll be an aj with a pi I. Now, recall the form of the projection operator. The projection operators are symmetric. They're always symmetric. So each of those is going to give a projection operator. So let me just write here, we're going to get a p ij. We're going to get 2 of them, and we're going to get minus 2I over omega, and we're going to get a del 3 of x minus y. So from the 2 non-trivial commutations, that seems like what we should get. And that's what I wrote in the notes too, so I'm even more confident. Yeah, if I put that j up, we just put that j up. So now we can do some integration. So here we have ai of k with I, a conjugate j of q equals what? Let's see, a minus I and an I here. We're just going to get a 2. We've got 2 pi cubed. The del 3 of x. If we integrate y, it's going to change this y to an x, and that's then the only y dependence. So now we have e to the minus I k minus q dot x, and we've done the y integration. Okay, and setting then integrating that, we get another delta function. We get a 2 pi cubed. The x integral gives a delta function in k minus q. And let's see, this bracket leaves us with a Pij. We integrated over that. We pulled out the coefficient, and the omegas become the same. So I think we just get an omega over 2 overall here. And so those go away, the 2 goes away, and we get an omega, a Pij, and a del 3 of k minus q. Hope this is tipped right. Yeah, you can see that, right? Let's see, the only thing that's funny is I seem to have lost an omega.
Yeah, you didn't pull out the omega we got from the bracket.
This guy here.
Yeah.
That omega is not there. So that omega, well, there was an omega here too. It went away. Good. Okay, thanks, Tyler. Okay, so now this looks good. The commutator of these two, I mean, we could put the I on the other side if we want. We get a projection operator. So if I whack this thing, if I whack either index with a K, the P is going to kill it. So this all lies in the plane orthogonal to K. We've got our delta function. Otherwise, basically, you know, A and A daggers coming out to raising and lowering operators again. So that's good. Do we have time for polarization vectors? How you doing? Let's let me ask. Are there any questions? You guys with this? Okay.
Just I guess the factor of I that we're using on the raising and lowering operators. That's just for convenience sake, just to make things roll nice.
Yeah. That's nothing special. I'm not even sure why I use that. There's a minus I that comes in the commutator, and it gets rid of that. Oh, yes. Oh, there's something very cool that happens. Thanks for asking that. I'd forgotten. So the transformation from A and pi to A and IA is a canonical transformation in phase space. That you know, so with E and M, that means, you know, there's actually no difference between working with A and a IA conjugate than working with the original A and pi. You know, we could canonically quantize these guys directly, which is that's really cool. So I can put hats on these guys without going through any of the A pi stuff at this point, because that's a canonical transformation. Isn't that right? Someone's meowing at me over here. So yeah, and you know, you can check that transformation actually is canonical. Let's see, is there an obvious way to see that? I do
notice,
yeah,
like it is.
This is the canonical commutator, right? Pij with del 3, that is the canonical commutator. So that's what tells you that this bracket is canonical. All right, you're muted, Tyler. I didn't hear what you just said, but yeah, that's.
I was just kind of nodding along and kind of talking.
Okay. Myself, so yeah. Cool. All right. Great. Okay. So polarization vectors. The thing we want to do here is very much like what we did with the Dirac equation. Okay. In addition to mode amplitudes in the expansion, we put some basis vectors, and so essentially we have 2 degrees of freedom left in these expansions, and what we want to do is write an AI for each one times some kind of a polarization vector for each one. So you know, we're going to have a sum over 1 to 2 degrees of freedom here. So we introduce a mode amplitude for each polarization of the photon field is what this ends up being. We can do that formally. I mean, relativistically. So in place of, right, so A alpha is going to have mode amplitudes little a alpha, And what I want to do is introduce some basically polarization vectors. We're going to replace this by some 4 vectors. What do I call them? Epsilon. And there are going to be 2 of those. And then each will have an associated mode amplitude A that's a function of K. So rather than writing these are operators as some kind of vectors, we're going to pull the vector part out and then give each independent polarization vector a mode amplitude. So we're going to sum this from 1 to 2. There are 2 degrees of freedom. And let's see. Yeah, it's not hard to choose some conditions on those basis vectors. Yeah, basically, well, we need some time-like vector T alpha. So, we pick a time direction, and our K alpha is, well, it's some magnitude times 1 and some unit vector K. And we want to choose these to annihilate those basis vectors. So we're going to choose A alpha, tau alpha equals 0, and epsilon alpha, K alpha equals 0. And then the wave mode is traveling in this K hat direction. So the polarizations are orthogonal to that direction. So this kills the time component. So this tells us that in this basis, E alpha is going to be 0 here, and something perpendicular to K in this space. And other than that, we probably want them to be unit vectors. So there are 2 such vectors, and we can pick them in a variety of ways, but not today because we've run out of time. But we can choose circular polarization. So one's the complex conjugate of the other, make those vectors complex. That's fine, circular polarization. Or linear polarization for a wave in the z direction, just choose them x and y. And that's a perfectly good pair of polarizations. But in this way, we define them relative to a particular choice of our time-like hypersurfaces and our wave vector K. Okay, ran out of time, ran out of voice. I'll stick around for questions. Otherwise, read on, and let me see, how far are we from, quantization. Quantization takes about 10 lines, half a page, and then we're into interactions. So I got to tell you, I'm racing to keep ahead of the class at this point because I haven't written this half of the book. So, I'm anticipating actually that the quantization details are going to, quantization of this is just putting hats on everything, and everything else just works. But for scattering, we've got to do quite a bit of work on the matrix elements. So we're going to look at a transition amplitude between some bunch of initial particles, some bunch of final particles, but we are going to massage the hell out of that thing. We are going to, drastically alter it, turning it into a whole mess of integrals times a vacuum expectation value of a bunch of time ordered fields. Then we need to prove Wick's theorem that we can change those time orderings into normal orderings plus some functions. And so there's quite a bit of story to go before we really actually draw our first Feynman diagram, but we're getting there. We'll start massaging that thing next week. Yeah, just a little bit to say about quantization here. And then, basically quantization is just put hats on everything I've already written. Write A here, write this with these vectors, write them that way, and then put hats on all the little a's, and we've quantized it. the A and A star become A and A dagger, and they're satisfying the normal commutation relations for raising and lowering operators. So we can describe the vacuum just fine. No additional difficulties. The hurdle here was handling the gauge, and we've done that. So questions, anything? I can stick around. I know some of you have to go.
This isn't a question, but just something to recommend before I go.
Oh yeah, sure.
Yesterday, the LHCb put out some new results.
Possible leptoquark, right?
Yeah. Just if anyone wants to look, it's really interesting.
Have you seen a good article on it? I've just read a couple of news clippings about it that aren't very precise. So
I managed to find one. I was just about to try and find it right here and post it.
Yeah. Okay. Yeah. Can you send it to everybody, or send it to me and I'll send it to everybody? Leptoquark. I can talk a little bit about leptoquarks. Well, I don't know if you're all rapidly attentive now. I could do it next time when everybody's here. But okay, quickly. Suppose you wanted to unify the standard model by saying, oh, there's one big symmetry of which there are parts. Well, you can fit SU3 in the corner of a 5x5, and you can put an SU2 down here. And there's actually one diagonal matrix that commutes with those. Those could be your U1. So the tightest kind of unification, a grand unification, this would be, of the standard model would be something like an SU5 theory, where this acts on the 3 quarks and this acts on the lepton doublets. So the SU2 acts on these and so on. But you've got additional particles here. And if you sandwich this between quark, lepton, lepton, what these do is they give you interaction terms that have a quark and say an X and a lepton. And what that would mean is that as an interaction term in Lagrange, that would mean that a quark could decay by emitting an X and give a lepton. Okay, that makes protons unstable, right? A proton could decay into a positron. So these particles are called leptoquarks. And okay, so protons are very stable, 10 to the 32 years or something. But 10 to the 35, maybe a few of them will go away. And leptoquarks would be one mechanism for that. Well, the current LHC result, which is about parts per thousand, not parts in 10 million yet, but seems to be holding. Oh, good. Thanks, guys. Yeah, I'd like to look at those papers.
Yeah, they're pretty interesting.
So a leptoquark could account for the anomalous data they're seeing. What they've seen is a heavy quark. What is it? A bottom quark, very heavy quark. Its mass is so much more than the muon and electron masses. You would expect basically equal probability for decay into electrons or muons via the weak interaction. But they're seeing an anomalously high number of decays into electrons rather than muons. And you could explain that with a leptoquark. There are probably a billion other explanations for it too, but you don't have to go far to say, oh, well, there could be leptoquarks. So that's pretty exciting. It's a potential new particle discovery at the LHC, and that's why they built it. So it's pretty exciting news. Yeah, thanks for sharing that, Eli. I appreciate that. And here I'm gonna.
Yeah, I figured this bunch would be interested in at least a decent amount. So
yeah, this is where we should talk about that kind of thing. Yeah, okay, I got the article. Great, thank you guys. And then let me get this other one. Yeah, okay, I've downloaded those. I'm sure there's a way to go back to the chat after the Zoom is done, but I don't know what it is. So I've opened those now, so I've got them. Great. Yeah, thanks. Yeah, that's pretty exciting stuff. Yeah, thank you, Eli. And, yeah, I'll be talking with you tomorrow afternoon, right?
Yeah, and
Yeah.
now I got to back up to teach. So
Yeah. Okay. I'll see you, Eli. Thanks.
Yes.
Yeah. So, any other questions, comments, new particles? What you guys got?
We'll see you next week.
Okay. I'll see you. Take care.
I had a question about the bracket, this new projection bracket we did.
New projection
anything-
bracket.
This canonical bracket that we did, we added this projection operator into it.
Oh yeah, the PIJ. Yeah, sure. What you got?
So I guess I don't know. I'm just in general. I guess I'm just. I mean, can we always define brackets by adding a projection, or like what's the condition where this projection? I mean, I get that it's like on the basis where it's 1, it's the delta function, but I'm worried about the zeros.
Yeah, well, yeah, we needed it to be 0 on the bracket side, right? Because derivatives of the brackets gave divergences of either a or pi, and those we really want both of those to be 0.
Yeah.
But imposing that condition on some generalization of a delta function, well, actually, the way you would define such a thing is by going to the Fourier transform and giving an algebraic condition and saying, okay, the Fourier transform, inverse Fourier transform of that is the function that we need. Right, so here.
Yeah.
Yeah, where did I put this? Yeah, so we're saying, have I got it up here? Let me just write it again. So we're saying that AI with PJ, sorry, with pi j, x and y, is the Fourier transform D3K of some matrix Pij and a right. So otherwise, a delta function k dot x minus y. So yeah. So this is some well-defined but curious object. You know, that's some projective function of x and y that is a lot like a delta function. So, we know how it acts because we've got the nice analytic expression for it here. But what is the Fourier transform of this matrix, which would otherwise be a delta function? Well, it's like, maybe it's some matrix valued delta function thing. But as the Fourier transform, it's just the matrix times a Fourier mode.
I guess I'm just worried why this would give us back Hamilton's equations. Just if we have this with this P operator. I mean, I guess I'm worried about a general operator. P makes kind of sense because it's locally like the delta function. Like it's one. It's one if you're in the space you care about. But so like what are we doing here? Are we like enforcing some type of like 0 on the bracket that we didn't expect if we did it in general?
Oh, exactly.
Like,
we're imposing di of the bracket equals 0.
Which is the Coulomb. This is from the Coulomb gauge, right?
That's the Coulomb gauge. So we're imposing the Coulomb gauge on the bracket.
I mean, is this like the energy step function type of thing that we did in the Earth? Like, but we're doing it.
Energy step. No, not an energy step. We're projecting to a subspace of some some fields, right? We're only allowing certain fields. So if we use this bracket to compute the Hamilton's, okay, see ya, Guillermo. If we use this bracket to compute Hamilton's equations, we will get Maxwell's equations in the Coulomb gauge.
Yeah.
So we've made a gauge choice here.
And I think that's what I'm wondering. This P is coming from the gauge choice, right?
Yes. Oh, absolutely. Yeah.
Okay. So, and that's why I related it to the E. Was that like the same thing when we were trying to make the choice that E was greater than 0? We were trying to make a positive energy gauge choice.
Way in the beginning, I remember. Yeah, we put a step function in E. We were just dodging the whole antiparticle thing, right?
Yeah.
But I put that in by hand because I didn't want to deal with negative energies yet. Yeah. But yeah, that step function doesn't really belong there. But this does. Yeah, we need this unless we do some other trick to handle the gauge freedom. I mean, there are other ways of handling gauge freedom, like putting a mass in. That breaks the gauge invariance, but it keeps pi 0 free. And then in the end, you take the mass to 0 and hope everything stays finite, which you can do that. And then there are other techniques. You can introduce to what are called ghost fields. So you introduce additional fields that more or less subtract off the degrees of freedom that aren't really there. And is it Faddeev-Popov ghosts? This falls into the general category of techniques for handling gauge theories, because with SU2 and SU3, it's even worse. You have a lot more gauge freedom, and you have to worry about how to quantize the system, hopefully without specifying the gauge, but also without counting it in your, you do a path integral, say, where you're summing over all states. Well, you want to sum over only physical states. So you somehow have to divide out some volume of phase space occupied by these spurious modes that don't really exist, that are just gauge. And so there are some covariant ways of doing it. And yeah, I don't know if we'll get into those or not. That's maybe this summer we can look into how to control gauge and more general gauge theories.
Yeah. Okay. Yeah. Because so P is also P is dependent on K, right? So that's where this is the gauge.
Yeah.
This is
which is why this integral is really funny.
Yeah, we gauged in K, and so our delta function, it's like we're trying to gauge the delta function, kind of. We're like we're redefining the delta function as the Fourier inversion of this.
Yeah, exactly what we're doing. So that's non-trivial because this does depend on K.
Yeah.
So I don't know what that becomes when you integrate it. Let's see, the K's. I suppose you could get the K's with some derivatives, right? So build this out of a Kronecker here is no problem. That just comes out. But the KK term, you could take derivatives with respect to K and pull those out. Although I'm not sure how you'd make them unit vectors. With derivative operators. That's sort of nasty. So that reduces it to worrying about a normalization factor. You'd have two, say, x derivatives of this for the KK, but then let's see. Yeah, if you wrote this, I'm not sure you can do that. Let's see, if I wrote that exponential as e to the minus I magnitude of k times a unit vector k. Yeah, see, that's going to be the wrong thing. No, that's not going to help. So if we wrote something like di dj of this integral d3k over, we would need magnitude of k squared e to the minus I k x minus y. So 2x derivatives pulls down to ki kj here. The minus sign, okay, so the I squared is going to go away with that. But now you're still not getting exactly a delta function here. it's got this funny normalization. So
Okay. Yeah.
I don't know what that integral is offhand. I mean, maybe it's not too hard to figure out.
It should be something, right? It looks like something.
Yeah, it's almost a delta function. Let's see if I were to.
Maybe
Huh.
it diverges even. Is it? I'm seeing. I'm seeing.
You know what it is. All right. So if I were to hit this with a D'Alembert, that pulls down that pulls down a k squared and gets rid of this. So I could write this as. You ready for this? On x, but that's going to sum them. So it's going to give a k squared, or sorry, Laplacian. Right, so a Laplacian on this is going to pull down a k squared, minus k squared. Okay, so what I want is di, dj, and then I want to invert that Laplacian with two signs, d3k e to the minus I, k dot x minus y. Okay, so this gives me a 1 over k squared in some weird sense. And so this is a delta function. So yeah, what I need is di dj over the Laplacian. So I have to invert the Laplace, solve the Laplace equation, right? Well, how do I do that? Probably a Fourier series, but so, this is in some suitable space, that's a well-defined differential operator. and that's about all I can promise you.
Okay.
That anyway, that's what it is if we insist on writing it in XY space. But then, let's see, what does that do? It might work. I don't know. Yeah, it should be divergence free anyway. And and we're going to subtract that from 1. Oh, yeah. That might work. I don't know.
We didn't do the 1.
Yeah, so
1 minus this.
sorry. Yeah. So it's a weird operator, but if I were to take a divergence of it, see this, it's this minus delta, right? We've also got a delta ij here, minus all that times delta ij. So that's, in some sense, that's our bracket, right?
With the inverse of the, maybe I'm being stupid, but isn't, let's see, it's okay. Never mind. Sorry.
Yeah. So look, if I take a divergence on, say, I'm going to get a partial here. Here, I'm going to get a Laplacian times a derivative over a Laplacian. The Laplacian cancels, and I get partial minus partial is 0. So formally, that works. It's just, I've got to, I take two derivatives of a delta function, and then I take the inverse of the Laplace operator on that. So what I'm saying is there's some phi that's equal to the idj of a delta function, and some phi ij. So that phi ij is 1 over del squared on that thing, whatever that is. So in principle, we know how to solve equations like this. We know how to solve Laplace equation with sources. So in some formal sense, we can assert that function exists. But if we actually want to write it, write a Fourier transform, right?
Yeah,
the Fourier transform of that is a perfectly algebraic thing.
It's looking like a Green's function. Maybe this is like a.
That's exactly what it is. Yeah, that's exactly what we're doing. Yeah, this is this is the Green function for some derivatives of a delta function. That's right. Yeah. So except for the di dj operator, yeah, that's exactly a Green function.
For the inverse thing. Okay, yeah, that's I think what I'm trying to get at is it's looking like our gauge condition is algebraic, but we're using it to fix the bracket, right? I mean, I understand why
Well,
why we got
yeah. By writing it as a Fourier transform, we have made the gauge condition algebraic. It was originally del dot A equals 0, a differential condition. That's awkward. So we want to turn that differential condition into an algebraic condition. We can do that in momentum space. And
yeah, and this is why we picked the Coulomb gauge, right? Because that's why this worked too.
yeah, Coulomb gauge makes it just a projection.
Does it work in other gauges, or does it get, or does it work at all, or does it get
there are other things we could do in other gauges. Let's see. Yeah, I don't know a lot of other gauges. You know, the Lorentz gauge condition only gets you halfway there, and we've already used that. You know, we're well, actually, yeah, in a way, we're getting back to the gauge conditions with you know, by choosing these polarizations orthogonal to two vectors. I mean, the orthogonality of epsilon with tau is basically the Lorentz gauge condition. That's yeah, that'd be like a, yeah, that's an algebraic version. Yeah, so that makes it, oh, wait a minute, which is it? No, it's the other one. It's orthogonality to K alpha. All right, so a Fourier transform makes the Lorentz condition into K alpha epsilon alpha equals 0. Yeah, so that's a Lorentz covariant gauge condition. I haven't seen a lot of other gauges used. I mean, maybe in a particular problem you want to structure it one way, but these are the most potent ones. The ones that get you the furthest with the simplest conditions.
Yeah. It seems like eliminating the time component of A was like pretty important for this quantization.
Mm-hmm. Yeah, because but that was the first problem we hit, is there's no pi 0 conjugate to A 0. Yeah. So right there you're in trouble. Now if you go, remember the electromagnetic theory we were writing? I played with that some more.
Cool.
Well, I asked whether it was the same as just complexifying normally E and M, and it's not. What happens? Okay, so you write E plus IB, and you can just add the two equations, and the two equations are almost the same, except for one source has the opposite sign. Remember, we had box of stuff is this plus this plus this, and some combination of these sources, and two of them were the same, and the third one had the sign flipped between the E and B, and so it didn't, the box of E plus IB depended on E minus IB, or it was really J minus IK or something. It depended on the complex conjugate of some of the sources, so it didn't become a single equation. So it's different than the complexification, even though it's really very similar, oddly enough. Yeah, it becomes that's interesting. It becomes so I wrote the sources as rho plus I sigma and J plus IK, and I wrote the field as E plus IB. So now I've defined, 3 complex fields where we had, 6 regular ones. And interestingly, the only thing that comes out with a conjugate is the J plus IK turns into, it comes out in one place, it comes out as J minus IK. Well, those are the same if K equals 0. So the complexification works if K equals 0. And what have we just done? We've removed the source for B.
Oh, that's interesting.
Yeah. So go forth and play, right?
Yeah, okay.
Yeah. So that there might be some interesting thing to say there.
Okay.
you know, or maybe it's just fun to play with. I don't know.
This is really interesting. I wish I had more time. Gosh dang it.
Yeah,
I guess that's what
I-
post coursework is for, huh?
I know how that goes. Yeah, let's see. What were you saying about Schwarzenegger?
Oh, no, that was just one of the Dr. Oh, I'm so bad with names. That taught E&M last year. Always teaches E&M. His name, atmospheric
Bella-
science.
Bella Fair or Bob Shunk?
Yeah, Shunk. That's one of Shunk's jokes, is that the curl of the curl is the Schwarzenegger, because he's so strong. It's so stupid.
Okay.
We just heard that joke like 100 times last semester, so I had to make it today.
Okay. All right. So when was that? Was that E&M 1 or 2?
Both. We saw curl of the curl in both, so that joke was lots.
Yeah.
But
When are they taught? Which semester is which one taught?
It was in proper order, fall, spring.
Yeah, fall and spring. Yeah. I'm wondering if I'm teaching. I'm teaching E&M 1. I'm doing it next fall.
Are you? Cool.
So how far did Bob get?
I mean, through the 2 courses, we got to wave solutions. Yeah, it was slow.
Yeah, I try to cover chapters 1 through 6 the first semester and 7 through 12 the second. Waves is chapter 7.
Yeah, we got to chapter 7. I bet our test was on end of chapter 7.
Not nearly enough.
No, I agree. I mean,
Yeah.
I might.
You can learn so much out of Jackson. I'll have to show you. It saves one of my copies of Jackson. The cover's falling off. It's probably my most used book.
Well, and part of what my problem with that, I guess I don't have any problems with that class, but part of the hang up was that we didn't really have homework. We just had tests. So he'd give homework, but it wasn't like do it. It was just like, you better know it before the test. And our entire grade was tests. So it's just like, I didn't really get a lot of E&M until the test came up, and then it was cram. So, I might just kind of eyeball some of your homework assignments next fall and do them too. Just
Josh did that. Josh took it independently from me. You're totally welcome to, sit in or do the problems or whatever. I don't know how easy it is to give you access to, if it's
Dr. Fells managed it last year. I was auditing. So, I mean,
okay.
we don't have to do it.
Is there such a thing as an official audit? Maybe we just have to add you through channels or something. I tried to, what was it? Josh was interested in sitting in on like this class, I think. And,
oh, damn.
I don't know, some class. I added his name to the class list in Canvas, but somehow he still didn't have access. So there's something more that has to be done. So, but I can figure that out. We can do that.
Yeah, there was Dr. Fells had some issue. There was something I remember. I could go back into our emails and look too, but he just somehow it worked. I don't know if it might have had to be a school email address, like a .aggie, but
okay. It's some little thing, right? I mean, I should be able to let anybody I want audit. That I don't know if they charge for that. Like $50 or $80 or something. I don't know. But if not, I can give you access to other stuff that's equivalent. Actually, I put everything on the physics server, and then I have Canvas access the physics server to pull it up. Okay. So all of our files for this class are actually on the physics server, not on Canvas. I don't bother to upload them to Canvas. I just link them.
Do grad students have access to that server? It's kind of, professors have their own private sections. Is that how it works?
Yeah, I think. Yeah, but I can give you addresses to link any of the files I've got on there, and I've got files for all of my classes on there. So, I can link you to anything that I've written, which is like way too much. I keep writing.
Right. Yeah, and I don't even know how much I'd need to learn, but I might just be curious. I mean, I got a lot out of that class, and and it's pretty tractable, classical E&M. It's kind of like all solved, I guess. But so it's mostly just the hard problems, getting into the nitty gritty, I guess. And the end chapters. I don't know about the end chapters. So I don't know. There's just, I'm always looking for analogies for systems, and it seems like having a bunch of E&M systems in your pocket is useful.
All right, yeah, here, let me find this. I can send you the link to my E&M pages right now, I think. Let me see what these look like. So notes, spring. Oh, I see. Okay, so the last time I taught this, all right, Shunk had taught it the semester before, so he skipped over green functions. So I started off with that. All right, here I can. Let me send you the link to this. Let's see. Alex. But let me also see if I've got another version of this that does the first semester too. That would be somewhat earlier. This. Oh boy. I don't know. It may be too long ago since I did it. Unless, there it is. Oh, okay. So, yeah, notes on chapters 1 and 2. All right. Yeah. Okay. The towards the bottom of the page I just sent you, there's a link to some very limited notes on the first couple of chapters of Jackson, and then also notes to my 3600. I taught E&M at the upper division undergraduate level, and I linked to a bunch of notes to those too. So that page I just sent you, that gives you all kinds of stuff on E&M. Didn't hear what you said.
No, brilliant. Yeah, this is good.
Okay. Yeah. So yeah, just go to the notes page. Yeah, way down at the bottom you'll find some more basic stuff. 3600. Yeah, that was a pretty good E&M course. I covered a lot of the basic electrostatics, magnetostatics there. And then the notes up top are my notes from the second half, E&M 2 graduate. So those follow Jackson. And I don't know, there's probably a homework page that shows what problems I assigned from Jackson. What's that?
Why was the final on March 2nd? Is that a typo? Is it May 2nd?
Yeah, that's probably a typo.
Okay, sorry to interrupt. I was like, what is it? Were you guys in quarters once? Like, oh my gosh.
Okay, midterm exam, March 4th.
Final exam.
I guess I forgot to change. That clearly should be May. I must have just forgotten, copied and pasted something and forgot to change a number. So that, yeah, that would have been May 2nd.
Yeah, it looks like we got to about, somewhere in this after the midterm. We did multipoles. I don't think we did any scattering. And we did relativistic E&M, but that was like.
Oh, okay. Yeah, and
so any of this
in E&M 1, did he do Green's functions?
Yeah.
Oh, okay. Because the year I taught this, he had not. He had skipped over Green functions.
Those poor kids.
Yeah. So I started off and did Green functions with them.
Well, maybe he did it the first one. Yeah, he did it the first one.
Yeah. Okay. Well, yeah. That's good. Yeah, he probably saw that I had gone and covered it for him and felt he ought to. It's just linearity. It's not really that hard an idea. So anyway, there you go. Feel free to ask questions on that, any of that, anytime.
Okay.
And yeah, you can audit the class in the fall if you want. You're welcome to sit in on any of my classes.
I might scare the kids may want a break from me, so I might not attend lecture to not scare them. But I may poke at what y'all are doing and look at some of the assignments and just play it by ear.
Yeah, sure. Yeah. So all right, I'll avoid Schwarzenegger jokes.
So bad. Yeah, kids will cringe. Don't do that. Lyle, Guillermo, and I'll just smack you.
Curl of a curl. I knew he told jokes. I didn't know they were that bad.
They're really funny. They are so bad. They are so bad. It's great.
That's okay. Yeah, you gotta joke around.
You do. And somebody's in the department has to be making the bad physics jokes. You're making good jokes. So
well,
Stoic is pretty funny. Tori's hilarious. So somebody's got to be.
Oh, that's good. Yeah.
I actually grew up down the street from Dr. Shunk. I didn't even know that. He lived on the same block as me.
Really? Yeah. Where was that?
Just in the same house he's at now, that yellow house up on Cliffside.
Oh, yeah. So you grew up in Logan?
Yeah.
Oh, wow. I didn't know that. Wow.
Small world, right?
Yeah. I wondered how you ended up back here.
I worked in JR's lab as a high school student and as a and one summer I came back for college. I just wanted a bum job. But
really? Oh, geez.
Yeah, small world, right?
Oh, that's great. You and Kip Thorne, huh?
Okay, there, guy. No, yeah, it's crazy that he went to Logan High too. I mean, I didn't even know that he went to Logan High though when I was going there. They don't advertise that there. They never.
Yeah, well, he's a little more liberal than the rest of the valley. I was on the honorary degrees and commencement speaker committee for 3 years, and then somebody left and they had me chair it for a year. And I got both him and his mother Allison honorary degrees that year and got him as the commencement speaker. And they have not asked me again.
Really?
That was a great commencement speech, though. It was wonderful. You can imagine. Yeah.
How long ago was that?
Oh, gosh. It's sort of the 10 to 20 year range. Everything seems like it was either 5 years ago or 20. I don't know. It was probably in the aughts, 2005-ish.
Before the Nobel Prize. It's cool.
Yeah, it was. It was before the prize. In fact, I at some point, who did I write letters for? I guess, as a way of encouraging the committee to get him in for the commencement speak. I said, this guy could get a Nobel Prize because of blah, blah, blah. And, because, we knew that, gravitational waves would eventually start showing some interesting stuff, right? And he has been, oh gosh, I remember him. I heard him first in, 1970. He and John Wheeler spoke at the APS meeting in Chicago, and I got down to it as an undergrad. And his whole talk was politics. There was very little physics in it. His hair was as long as yours is now at the time. And he was.
Nixon's in office, right?
He's what?
Nixon was in office.
Yeah. Right. Yeah, those were the days, huh? Yeah, Vietnam was in full swing and just all of that stuff. So yeah, he was radical, physics, politics. I forget what he was saying, but since then Joseph Weber talked at that. Joseph Weber at that meeting announced the first detection of gravitational waves with the Weber detector, the Weber bar, and it was wrong, right? It was 10 to the 20th times 2, or I forget, a large factor. What he had done is he was arguing that the sensitivity would go as the square of the number of atoms or something like that, and it doesn't. It goes linearly. And so the detector was not nearly as sensitive as he had thought it was. They're still building Weber bars, and they'll eventually be able to detect waves. But he was there and he made that announcement, and Kip was there, and John Wheeler probably talked about black holes. But subsequently, Kip got into it with Weber, and he has made most of his career since in identifying astrophysical sources for gravitational waves. So, looking systematically at everything that could produce a detectable gravitational wave, and quantifying exactly how strong a wave is and what kind of frequencies. So, LIGO has made heavy use of his group's theoretical work describing sources for that detector. So it's really this importantly joint effort between his theoretical calculations of waves and the detector's ability to actually see them. And so it's a much deserved Nobel Prize.
Yeah. You definitely, sorry, go ahead.
And he gives a great commencement speech.
I don't think I ever saw his Nobel commencement speech. I should probably YouTube that. Huh?
Oh, yeah. It's got to be out there. I don't know what he did for the Nobel Prize acceptance.
You definitely probably won't remember, but when he came and talked to Logan,